Today we're going to learn about acid-base reactions right here. Acid-base reactions. So you'll learn about acids and bases. And right here, acids tend to taste sour and can change the color of a plant dye. They can react with some metals to form hydrogen. Next, we have bases. And here are some properties of bases. They are slippery. Soap is made with bases, and they taste bitter. Let's go back to these tastes a little bit. So lemons taste sour. Lemons are acidic. If you've ever had tonic water, that would be basic. It tastes bitter, and it can change the color of some plant dyes. There's something called the Bronsted-Lowry acid-base definitions. We have 3 different definitions, but we're just going to go with the Bronsted-Lowry definition for this class. And that definition is that acids donate protons, bases accept protons. Protons are H pluses. So if you think about an H plus that has 1 proton, if just an H would have 1 proton and 1 electron. So an H plus would be the proton and electron minus the electron, which would give you just a proton. Hence, NH plus is considered just a proton. All right, we're going to talk about conjugate acid-base pairs. This would be a pair of an acid and a base paired together. The acid has 1 extra H plus compared to the base. When I ask you to identify acids and bases and their conjugates, the acid and base would be the reactants. Just the acid and base would be considered a reactant. The conjugate acid and base would be considered the products in a reaction. So we're just going to look at how do you identify a conjugate acid-base pair. We said the acid has 1 extra H plus compared to the base. So if this is our acid, this has an extra H plus compared to the base. So the base, I need to take away the H plus and take away 1, because I'm taking away an H plus. Take away 1 from the formula. So I take away an H and I take away a 1 from the charge, gives me ClO1 minus. Try these next ones on your own. So go ahead and pause the video, try to fill these in, or you can listen. NO2 minus, the acid has an extra H plus, so that means for the NO2 minus, I'm going to add an H plus. You can fill this in now if you think you know the answer. Would be H, we add an H, and we add plus 1 to the charge. Now this one, it's not too tricky. Take away only 1 of the H's. Just take away 1 of these H's. We're left with 1 H. Take away 1 from the charge, and we get, you can fill this in on your own, HCO3, 1 minus. Now we're starting with the base. Here's my base. And now to get to the acid, I have to add an H. So I would have how many H's? 2 H's. I have to add 1 to the charge, and so my charge would be -1. Hopefully you got that. So you'd have H2PO4 minus 1. If you ever see just a minus, that means -1. If you ever see a plus with no number in front of it or behind it, that's +1. All right. HCO3 1 minus is my acid, and now I want to get to the base. The acid has an extra H plus, so I have to take away an H plus to get to the base. Take away 1 H, leaves me with no H's. Take away 1 from the charge will give me a what charge? Let's look. A -2 charge. So we get CO3 2 minus. So that is it right now for conjugate acid-base pairs. It's an acid and a base that look almost exactly the same. They just differ in an H plus. So the charge is different by 1, -1 versus 0. And the number of H's is different by 1. 0 H's versus 1 H. Okay, reactions involving acids and bases. These are done exactly the same way from the last video, video 4.2. You might want to have those notes out while you're doing this section. We're going to start right into a problem. So we'll start, we have an aqueous solution of sodium hydroxide, that's a base, and sulfuric acid, which is an acid. First, you have to figure out the name. Actually, you don't have to figure out the name. You're going to have to figure out what this name means. So sodium and hydroxide, figure out what the ions are. I'm going to open this up in a moment and show you, but let's see if you can figure those out. Sodium and hydroxide, you might want to look on your polyatomic ion sheet. In sulfuric acid, we would have sulfate because it goes to 8 and H+. So my ions are Na+ from the sodium, OH- from the hydroxide, H+ and SO4 2- for the sulfuric acid. I don't need the whole formula right now. Okay, when we have reactions, when we're predicting our products, if we have ionic substances or acids, we're going to just switch the negative ions. So this OH1- is going to switch places with the SO4 2- to figure out what our products are, right there. So I will have the Na +1 stays in the same place. These are going to be my products. The SO4 2- switched places with the hydroxide, and the hydroxide comes over here to be with the H+. Now we have to balance the charge to find the subscript. So when I put these together, sorry, the Na and the OH together, I have one of each. When I put these together, I need to have how many H+ to balance out the -2? I need to have 2 H+. So this would be H2SO4 when I put those together. Those are my reactants. Now my products, I have a +1 and a -2. So how many Na+ do I need? 2. This would be Na2SO4. And this would just be HOH, which is also known as water, HOH, H2O. So my NaOH is this right here. The H2SO4 is these balanced to add up to 0. This balances to 0 with Na2SO4. This balances to 0 with HOH, which is the same as H2O. I'm just writing this way for now so you can see we have an H+ and an OH-. Now we have to balance this. You can try to balance that on your own. I'm going to show that to you in a moment. And there you have it. There's your balanced equation. Okay, let's try that on another one. Okay, so first we have to identify what our elements are, what our ions are, sorry. So we have to identify the reactants and charges of the ions. So we'll have Ba2+, OH1-. Phosphoric acid has H+ because of the acid, and phosphoric would become phosphate. So we have PO4 3-. Those are my ions in the reactant particles. And then to predict my products, for the products, I have to exchange the ions. You don't have to always do it this way. I'm just going to, in this example, switch the PO4 3- with the OH1-. You could have moved the places of the H+ and the Ba2+, but I'm just trying to be consistent with the previous lecture. So we switch the places of the negative ions. So my reactants will be these put together. My products will be these put together. You might want to pause this. I'm going to show you what they are in a moment. Here you go. So the +2 and the -1 gives us BaOH2. The -3 and +1 means we need 3 H+. So we have H3PO4. These were our reactants. These are our products. So the products, to balance this out, I need 3 Ba2+ and 2 PO4 3- gives me this formula. 1 H+, 1 OH- gives me HOH, which is the same as water. Now I balance it. You can take a moment to pause and balance this, but I'm going to show this. There's our balanced reaction. Notice I'm writing water as just water here, not as HOH. Okay, we're going to move on to ionic and net ionic equations. So first we just got our molecular equations up here. Oh, let's put that in red. There we go. Okay, so we have our molecular equations, and now we're going to get the net ionic equations for these two reactions. There's something you have to know about acids. You'll have to memorize this. Strong acids split apart. Weak acids stay together in your ionic and net ionic equations. So this is, you do these the same way as we did our double displacement precipitation reactions, but in terms of what breaks apart and what stays together, you need to know strong splits, weak stays together. These are the 7 strong acids we're going to work with in the class. You don't have to memorize them at this point or this year. I'll always give you the 7 strong acids, but it's a good idea to try to remember them. And we have a little saying to try to remember these. We just read it out as we see it. Hibber, Hickel, High. Hano, Hio, Hickelo, H2SO4. So real fast it goes Hibber, Hickel, High, Hano, Hio, Hickelo, H2SO4. And that gives us our 7 strong acids. 3 of them have 4 oxygens, 3 of them have no oxygens, and the middle one has 3. So 3 on each side of the HNO3, and the HNO3 has 3 oxygens. So there's 3 strong acids to the right of HNO3, 3 strong acids to the left of HNO3, and the middle one has 3 oxygens. Okay. I'm repeating this right here. All acids that are not strong are weak and do not split. So if you have anything that starts with an H and is not one of these, you will assume that that is a weak acid and it doesn't split. So for instance, right here, the H3PO4 starts with H, so we know that's an acid. It is not one of these acids, therefore this H3PO4 would not split. And we'll go over that when we do that problem. So number 1, this is the one we just did right here. We're going to take this molecular equation and put it right here. This is the same molecular equation as what I just had in example 1 above. Now from the last lecture you learned what you first do is figure out who splits and who doesn't. And I'm telling you right here who splits and who doesn't. Sodium hydroxide is soluble, so that will split. Sulfuric acid is, oh, there's one of our strong acids, it will split. All alkali metal ionic compounds, or ionic compounds that contain alkali metals, are soluble. This one splits. Water is a molecule. Water never splits. Molecules don't split. Now I say that acids are a special case, of course. Okay, so let's see who splits. There we go. This is what we just spoke about. These 3 will split. This one does not and comes straight down. Now for your ionic equation, remember the coefficient applies to everything in there, and we multiply subscripts by coefficients to get our ions. And subscripts themselves come up to the front. So the coefficient here is 1, so I had 1 times 2 H pluses. Sulfate, you have to realize this SO4 is a whole unit. I can't quite highlight it. That SO4 is an entire unit by itself. You could try this on your own. I'm going to show you the answer. So the 2 applies to both of the ions, 2 Na pluses, 2 OH minuses. This 2 is multiplied by the coefficient to get 2 H pluses. That 4 is part of the sulfate, so I don't put that in front or anything. This 2 becomes a coefficient because I multiply the coefficient of 1 by this number 2 to get 2 Na plus. And the waters come straight down. Spectator ions, the things that appear on the left side and the right side. Here you go, that's what we had. Those are our spectator ions. We're going to cancel those out to get our net ionic equation, which you should be able to figure out on your own. You can pause and look at it. Okay. When we cancel out these spectator ions, we're left with the hydroxide, the hydrogen ion, and the waters. Notice we have a common factor of 2 in here, so we can simplify this into 1 hydroxide, 1 H plus, making 1 water. All right, next example. That was the second one we did above. I just took this molecular equation directly from right here. I just copied that straight down to here. Now we're going to do the same thing. You have to figure out who splits, who doesn't. And I have it summarized here. We'll talk through it. Barium hydroxide is soluble. It splits. H3PO4 is not one of our strong acids. H3PO4 is not going to split. It will come straight down. Barium phosphate, from your solubility rules, this stuff is not soluble, comes straight down. Water, is a molecule, comes straight down. So the summary of what these items are going to do, I've written here. You could figure that out on your own as you go through these. Think about solubility rules and weak and strong acids, and molecules always stay together. They do not split. So our ionic equation, this 3 multiplies to both the barium and the hydroxide, so you should be able to figure out you're going to have 3 Ba2 pluses. I'll show you it in a moment. You can write it down as we go. Hydroxides. I have 2 hydroxides in one formula unit, but I have 3 of these, so I have a total of 6 hydroxides because of the 2 here and the 3 here. This comes straight down, straight down, straight down, so that part is simple. There you go. Spectator ions. There is nothing repeating on the left side or on the right side, so our ionic and not ionic equations are the same. That happens. That's why I left this on your handout. Okay, last example. This is a whole new problem. We have to go through that first part of figuring out what your molecular equation is. I've got that written down here, but we're going to go through the process of how did we get that? Where did it come from? So first, we have to identify the reactants. Whoops. We have to identify the reactants and the charges of the ions. So you can look at that, try to figure that out on your own. I'm about to show it to you. You can pause the video. We have the barium hydroxide. Those are our 2 ions in there. Nitric acid would have H plus because it says acid. Ic goes to H, so I also have nitrate. I'm going to switch the place of the negative ions to find out what the products are. Okay, notice I just switched the places of the negative ions. And that will tell me what my products are. So one of the products will be barium nitrate. One will be, if you can tell, you've seen this a bunch of times, that's just our pretty old water. So you should pause this and try to do this on your own. I'm going to show you the reactants and the products. We just have to make these charges add up to 0. It's a common theme in chemistry. Charges have to add up to 0 unless we have a charged particle. And there is your unbalanced molecular equation, which we have to balance now, and I'll show you the answer to the balancing in just a moment. You can figure it out on your own and fill that in if you'd like. Notice I've turned the HOH into water. This is usually easier to balance if you leave the water as HOH, because you'll recognize this OH is coming from the hydroxides. This H is coming, oops, that single H there is coming from the H in the nitric acid. Okay, we have our balanced equation. Now we're going to go through how to get our ionic and net ionic. So, got to figure out who splits. Barium hydroxide is soluble. That splits. It'll give us 1 Ba2 plus 2 hydroxides. HNO3, you got to check your list of strong acids. If you do, let's go check. Oh, there we go. HNO3 is a strong acid. So HNO3 will split. We had 2 HNO3, so I will have 2 H pluses and 2 NO3 minuses because that 2 applies to everything in the formula. Barium nitrate. Nitrates are always soluble. That splits into a Ba2 plus. And how many NO3 minuses? 2. Hopefully you got that right. 2 NO3 minuses. And then waters. Do we split waters? Do we split molecules? No, we don't. So this is what the first line should look like. The first 3 items split. The water stays all together. And here's our ionic equation. So we have to find our spectator ions. Well, you should notice barium is on the left side as a 2 plus ion and on the right side as a 2 plus ion. So there's a spectator. Is there anything else? I can't find anything. Can you? Oh, there it is, the nitrates. Those are also repeating themselves. Those are that's our other spectator ion. So we have our 2 spectators. We will cancel those out to get the net ionic equation. You can fill this in on your own, pause the video, or just copy this down. Here we go. Okay, and again, we had that one where you could simplify the equation you got. There's a common factor of 2 in all of these. So we simplify this to hydroxide, and H plus makes water. Okay, last little tidbit. Sometimes you will see this word monoprotic acid. It won't have the quotes in there. I'm putting the quotes in so that you know this is something new for you. So monoprotic acid, mono means one. Protic, protons, one proton acid, 1H plus in the formula. HCl, HBr, HNO3, these are all monoprotic acids. Now, if you have two in the formula, I've given you a bunch of examples. Any idea what that might be called? It's called a diprotic acid. Now, I want you to look through all of this, the video, the notes you've taken, and see if you can find a triprotic acid. Let's look through. What do you think triprotic means? Three protons. Oh, there it is, right there. H3PO4. That would be a triprotic acid. And you are done.